Hello! My name is Brie, and this video will be about the thermal properties of matter and will be about a scientific solution to a mundane problem. My Keurig brews its coffee way too hot for me to drink right away. I have to wait at least half an hour before I can even start to sip it. What I like to do is add ice cubes, but even though instinctually I know about how many to add to get it to the temperature I want, it's all just guesswork, and sometimes it ends up too cold or it waters it down too much. But with my knowledge of physics and the heat equation, I can find out exactly how much ice to add to get it to just the temperature that I want. On the largest cup setting of my coffee maker, I get about 300 milliliters of coffee. And when I take the temperature of the cup, my instant read thermometer tells me that it's a steamy 78.6 degrees Celsius. What I would like is for my coffee to be a warm, not hot, but drinkable 50 degrees Celsius. In this situation, we have two interacting systems, the heat of the ice and the heat of the coffee. For the purpose of this demonstration, we'll say that the coffee ice system is closed, which means that no heat is lost, and that the heat of the ice plus the heat of the coffee adds up to equal 0. To get from the frozen ice and a hot coffee to a nice drinkable beverage, 4 things need to happen. We need to increase the temperature of the ice cube from -20 degrees to 0 degrees. Then, while it's at 0 degrees, we need to convert the ice to water. Then we need to raise the temperature of the water to 50 degrees, while also lowering the temperature of the coffee to 50 degrees. When raising or lowering the temperature, we can equate its heat to its mass times its specific heat and times its change in temperature. When we change the phase, such as changing ice into water, we equate its heat to its mass times its latent heat of fusion. In this last step, we'll say that the specific heat of the coffee is the specific heat of water, even though there is also milk and sugar present. What we want to know from all of this is how much ice, its mass, should be used to cool the coffee to the desired temperature. Adding these all up, and with some basic algebraic manipulation, we find out that about 0.062 kilograms is needed. Let's see if this all works. After brewing out the coffee and taking its initial temperature, I then used my food scale to measure out the mass of the ice that we had found in our equation. I then stirred it around with the thermometer until the ice had completely melted. As you can see, this is pretty darn close for an imperfectly closed system, kitchen measuring instruments, and ice that had already started to melt. 51.2 degrees. You can now take this demonstration and use it to make your own perfectly temperatured coffee. Bye!